Good morning, girls. Today we are going to discuss about another kind of data structure, that is trees. Actually, these data structures are classified into two categories. One is linear and the other one is non-linear. So the data structures, whatever we have learned till now, will come under linear data structures. So the data structure which you are going to learn now is a non-linear data structure. So first we will try to understand what linear and non-linear data structures are. See, a data structure is said to be linear if its elements form a sequence or a linear list. I mean, they are arranged in a sequential format. I mean, they come one after the other. Uh, they will have only one unique successor and one unique predecessor. So for example, if you take 5, 6 and 7, for 6, 5 is the only unique successor and 7 is the only unique predecessor. So this is called a linear list. If you store them in an array or linked list, whatever kind of data structure you use, if you store using this data structures, they will have this kind of order only, one unique successor and one unique predecessor. So in memory, we represent these linear structures in two ways. One is linked list and the other is arrays. So already we have discussed in detail about this linked list and arrays. So next, coming to what are non-linear data structures. See, non-linear data structures are used to represent the data containing hierarchical or network relationship between the elements. What do you mean by hierarchy? See, what is hierarchy actually? In a family, you have generations like grandfather, great grandfather, and grandfather may have 3 children and children of those. And if you take the relationship between these people, so it becomes a hierarchy. I mean, the lineage is coming from the earlier generations to the uh, later generations. So this is what is represented the best through these non-linear data structures, which are nothing but trees and graphs. So when you want to represent data in the form of hierarchies or in the form of networks, then you will use non-linear data structures, and the best examples for these two are of non-linear data structures are trees and graphs. So in non-linear data structures, every data element have more than one predecessor as well as successor. So this is the main difference between linear and non-linear. So in linear, we have said that it will have an element will have only one unique successor and one unique predecessor. Whereas in non-linear data structures, you will have more than one successor and more than one predecessor. They do not have any linear sequence. So that is the reason they are called non-linear data structures. They don't have any linear format. They don't follow any linear sequence. So they are called non-linear data structures. So what are the uses of these non-linear data structures? They are used uh, most useful, or we find them more useful in expressing complex relationships between linear data structures. So you can establish relationships between two linear data structures with the help of these non-linear data structures. So when you want to represent a hierarchical relationship, then you will use trees. When you want to represent network relationships, then you will use graphs. So what is hierarchy? Say here you're seeing the example family trees, or like grandfather, father, and their grandchildren, like that, or positions in an organization like um, employee and manager, general manager, CMD, like that. So hierarchy positions in organization can also be represented in the form of a tree. So a tree is a non-linear data structure. It is easy to maintain and also manipulate data in many applications. So instead of storing data in the form of a linear data structure, if you store it in like a non-linear data structure, it is more easy to maintain as well as to do the calculations or manipulations on the data. So we are taking the example of an operating system. Say here, my computer contains all the drives in your it shows all the drives in your computer. So if you take the representation or a chart like graphical representation, what we say till now, but now onwards we have to say it as a tree. So this is how it looks like: A drive, DE drive, C drive, and what are all the folders and subfolders or files in these um, C drive. If you go on representing them, it looks like this. So you can represent more number of files in an understandable format with the help of this linear data, non-linear data structure, that is tree. So, the what are the common uses of this trees? First one is manipulating the hierarchical data. So here you can see the hierarchy. Where is word? Where word is found in office, and where you can find office. Office is found in program files, and where program files are, they are in C drive, and where C drive is located in my computer. So this is hierarchy of the files located or present in your computer. So if you want to manipulate data, so it is best represented by using a tree. Next, making information easily searched. So searching for a particular data is very easy when you use or represent your data in the form of trees. So this we are going to see how this easy in detail in our next classes. So manipulating sorted lists of data. So when you are storing lists of data in a sorted form, you can do more number of operations comparatively when they are stored as non-linear structure when compared to linear data structure. So these are the common uses of trees that you can find. So, so you can call tree as an acyclic, directed acyclic graph. So what is a graph, and why do we are calling it as directed acyclic? So we will see all these terms are in the next points in the coming topics. So see, first we have, before going to learn what a tree is or how we can construct a tree and how we can traverse through it, first we have to learn some basic terms which are used frequently or which we use to define these trees or graphs. So the first thing is a general graph is what nothing but a set of two sets. One is set E and set E. So what is set E? Set is nothing but a group of or set of vertices, and E is set of edges. So you can view tree as a restricted graph. So first we have to learn what a graph is. So that is what we are doing here. What is a graph? It is a non-empty set. Non-empty, I mean it has some values. Non-empty set V and a set E. V represents a set of vertices and E represents set of edges, and a mapping from set E to set V. So a graph contains all these. So what are V? See, V is the set of nodes, also called as vertices points of the graph. So in linked lists also we have seen nodes, right? So node is where actually the data is there, stored. So here also we have nodes. They are also called as vertices or vertices points. And E is the set of edges of the graph. I mean how these vertices are connected to one another or each other. They are connected to each other through these edges. So the set E represents the edges between these vertices. So for finite graphs, so V and E are finite and they are limited in number. So you can represent a graph as uh, a combination of V and E, vertices and edges. So yes, adjacent nodes. So what is an adjacent node? So we have to learn, I mean, try to understand this because we are going to use these terms in detail, I mean, in next classes. So what is an adjacent node? So if an edge E is associated with a pair of nodes A comma B, where A comma B belong to B, then it is said that the edge E joins or connects the nodes A and B. Any two nodes that are connected with an edge are called adjacent nodes. So if you try to put 2 points A and B and try to connect them with an edge, so A is adjacent to B because A is connected to B through this edge. So that is what is said here. So if E belongs to set E, and it is drawn between two nodes A and B, which belong to set V. V is nothing but a set of vertices. So then E is said to join or connect A and B. So these two nodes which are connected by this edge E are called adjacent nodes. Directed and undirected graphs. So what are directed graphs and undirected graphs? So we have seen what a graph is. A graph is nothing but a collection of vertices and edges. So G of V comma E. So an edge is directed from one node to another node is called a directed edge. Whereas an edge that has no specific direction is called an undirected edge. So if you see here we are pointing the direction from edge 1 to, I mean, point vertex 1 to vertex 5. So we are pointing it through an arrow. So we are giving it a direction that here the movement is from vertex 1 to vertex 5. So when you specify the direction like this through an arrow mark, it is called a directed edge. If you don't specify any direction like that, so here if we didn't specify, we'll see what are all these in detail next. So if here we didn't specify any direction, I mean it can move from A to B or B to A. In such a case, the edge is called undirected edge. So a graph where every edge is directed is a directed curve, is called directed graph or diagraph. So you here have to specify the direction of each and every edge. So then it is can be called as directed graph. So if you don't specify any direction like that, then it is called undirected graph. So if some edges are directed and some are undirected, then that is called a mixed. So these are the three types of graphs you have. One is directed, the other one is undirected, and the third one is mix. So if you specify the direction of the edge, all the directions, all the edges in the graph are specified with the directions, then it is a directed graph. If you don't specify any directions, they are undirected graphs. If you use, for some edges you specify the direction, and for some, if you don't, then it is called a mixed graph. So see, so here the examples are given, like if you are representing only one-way streets, then it is a directed graph. If you are representing it two-way streets in a graph, then it can be treated as an example for an undirected graph. And if you represent both of them together in a one graph, it is a mixed graph. Like it contains both directed and undirected edges. Next, if we take a set B comma E, which represents a graph, and belongs to capital E, which is a set of edges. This edge is between A comma B. So see a directed edge associated with an ordered pair of nodes. Then edge E is said to be initiating or originating in the node A and terminating or ending in the node B. Say for example here, if you take this as A and this as B, here the edge is starting from A, originating, starting, and it is culminating or ending or terminating here in B. So that uh, edge is called, the edge A is called initial node, and the edge B is called terminal node. And this is called, the origin and termination of the node from A to B is called incident. See, an edge E belongs to E that joins the nodes A and B, be it undirected or directed, is said to be incident to the nodes A and B. So it is formed between the edge is there or exists or is available between nodes A and B. In such a condition, it is called incidence or incident. It is said to be incident between the nodes A and B. So an edge of a graph that joins a node to itself is called a loop. So if a node joins to itself, say if this node joins to itself, so that kind of an edge is called loop. So for a loop, the direction has no significance because it will be connecting to itself. Whether it comes in this direction or this direction, it doesn't make any sense. So the no direction is needed in case if it is a loop. Next, parallel edges and multigraph. So what are parallel edges? See, in this graph, for each node, there is only one edge between any pair of nodes. Say if the graph has only one edge between any pair of nodes. If you see between these two or these two or these two or these two, whatever, if you take at any point of time, if you consider two vertices, there is only one edge between those two nodes. In the directed edges, the two possible edges between the pair of nodes that are opposite in direction are considered distinct. So yes, if they are, see for example, if I have one more edge between these two nodes, and the direction of that edge is this, and the reverse of this edge, then they are not same, they are said to be distinct. See, but here you see, if there exists more than I mean two edges between a node, they are called parallel edges. See here you have three edges, one, E1, E2, E3 between vertices A and B. See, A, B, here you're having three edges. One is this side and one is this side, and the third one is without a direction. So in such case you call them as parallel edges. A graph that contains parallel edges is called a multigraph. So when you are having more than two edges between any two nodes, then they are called parallel edges. And if a graph contains parallel edges, then it is called a multigraph. If it is not containing any parallel edges, I mean it is having only two mm, edges between any node, between any two nodes at any point of time, then such a kind of graph is called simple graph. So these all the terms can be asked as a simple, I mean what you say, for your internal exam or small short answer questions. Next, weighted graph. So what is a weighted graph? A graph where weights are assigned to every edge is called a weighted graph. Weights can be also be assigned to vertices. So if you give some value to this edge, I mean for example, if these are if you are representing a map, these are two different places on your map, and you are putting some value on this edge which shows you the distance or which specify the distance between these 2 points, so that if you consider this graph, then it becomes a weighted graph. So if you assign some value to these edges, see, these are names, these are not values. The name of this edge is E5 and the name of this edge is E6. So you can't consider them as weights. So you assign some weights. See, as I said, if you are counting, you are measuring the distance between these two nodes, you can put as 4 or 5. Then that particular value is called weight. So you can give weights to edges, you can give weights to vertices also. See, a graph of areas and connecting nodes may be assigned weights such that the distance between the cities is assigned to edges and area population is assigned to vertices. So we have said that weights can be given to edges and weights can be given to vertices also. So if you take this as a graph of a city, so the roads and connecting are these edges, and the distance of these roads is the weight of that edge, and the area at that particular population at that particular area is the weight of that vertex. This is about your weighted graph. Null graph and isolated graph. So what is a null graph? A node that is not adjacent to any other node is called an isolated node. That means if you are not connecting it to other edge, I mean other node through an edge, so it will be looking like this. So in such a case, this node is called isolated node. A graph containing only isolated nodes is called a null graph. So this is the example for a null graph. So if you have nodes here A, B, C, but they are not connected to one another using edges, so there are no edges, so in such a case it's called null graph because they are isolated nodes. So the set of edges for an empty set is a empty set for this null graph because there are no edges between these nodes. So automatically this edges set is empty. Here is an example. These four or five people are students. These people are sharing books with each other. A is sharing book with B, B is sharing with C, and D is also sharing with A. because there is no direction specified here. It is an undirected graph. So the sharing here is happening between these four only. Though E is a student of this class or a part of this students, there is no sharing between, I mean, and no bookshell is shared with this E, so there is no edge between, I mean, from B to E or D to E. So this E has become the isolated vertex. So it's not a null graph to happen. This is a graph but with an isolated vertex. This is a null graph because there is just no edge between any of these nodes. But here in this graph there exists some nodes between these edges, but only this particular node is not having any connection with these nodes. So this is called an isolated vertex. So in the next class, we'll see what degree of a vertex is, and next paths and circuits, all these in detail. So once we finish this basic terminology, we will move on to tree, what a tree is and how to construct a tree, how to draw a tree, how to traverse a tree. It will be very much interesting. So if you have any doubts, ping me in the group.